This module will provide a closer look at some important terms, concepts, and tools in project quality management. There are some terms that are important to differentiate between in project quality management. The first set we will look at is prevention and inspection. Prevention is the act of keeping errors out of process, therefore reducing defects in deliverables. This is the key theme in the manage quality process. Inspection is the act of keeping defects out of the hands of customers. This means catching any defects that might exist before delivery or stakeholder inspection. This is the key theme in the control quality process. Another pair of terms to compare and contrast is tolerance and control limits. Tolerances are a range of measurements that have been determined by project stakeholders as acceptable. Tolerances are more closely related to results, such as deliverables. For example, a measurement, such as a temperature, may have a desired result of 78 degrees, with tolerances of plus or minus 2 degrees. A result outside of the tolerances would be considered unacceptable. Control limits are a way to measure the statistical stability of a process, meaning, does the process repeatedly produce consistent results? Control limits are more closely related to a process. Let's examine control limits by looking at a control chart to better understand the purpose of control limits. The control chart is one of the 7 basic quality tools. The purpose of a control chart is to measure the repeatability of a process. Consider an assembly line that creates automotive parts, such as a braking system. The assembly line is a process that has been designed to create the exact same results every time. If it does not, the process is not well controlled. In the center of our control chart will be the average of all data points. Above and below the center line will be the upper control limit and lower control limit. By default, these will typically be positioned at plus and minus 3 standard deviations from the mean. Statistically, this represents 99.73% precision. However, customer specification limits can be set to be more or less stringent. Measurements reflecting the output of the process will be plotted on this chart. For example, the diameter of a pre-drilled hole. There are 2 scenarios to consider that may indicate an issue with the process. The first scenario is when a data point falls above the upper control limit or a data point that falls below the lower control limit. When a process produces a result too far from the mean, we say that the process is out of control, meaning the assembly line is not producing consistent results. If the process is not consistent, we are likely to keep producing more defective parts. Therefore, when a control limit is exceeded, standard practice is to stop the process, investigate the cause, and fix the process before resuming. The second scenario is when 7 data points in a row fall on the same side of the mean, also known as the rule of 7. Even when all of the data points are within the control limits, the rule of 7 can indicate a process that may be trending out of control. Statistically, the data points should be randomly distributed across the mean, so it is very unlikely that 7 in a row would fall on the same side. This could be an indication that the process is slowly changing. Imagine a piece of machinery on an assembly line slowly falling out of calibration. By pausing and fixing the process, defects can be avoided. Therefore, when the rule of 7 is experienced, we say that the process may be out of control and it should be investigated. Typically, a control chart may be developed in the control quality process as a quality control measurement and then analyzed in the manage quality process. Another pair of terms to distinguish between is precision and accuracy. Precision is the degree to which a set of measurements, or the result of a process, produces similar results. In contrast, accuracy is the degree to which a set of measurements is close to the desired goal or measurement. Imagine throwing a set of darts and aiming for the bullseye. After throwing several darts, you find that they all hit the upper left-hand corner of the board. While they were not particularly close to the bullseye, they were all within a square inch of each other. This set of throws may be considered to be precise, although not accurate. Next, a friend throws several darts, all of which were closer to the bullseye, but were more scattered, covering about 5 square inches. These throws may be considered more accurate, but less precise. It is useful to understand that a set of measurements can be precise but not accurate but not precise, both accurate and precise, or neither accurate nor precise. Another set of terms to compare is attribute sampling and variables sampling. These terms can be used to describe how results will be measured. In attribute sampling, results will be measured on a pass-fail basis. Either the deliverable conforms or it does not. In variables sampling, results can be measured on a continuous basis. For example, server availability may be measured at 95%. It is useful to consider how stakeholders will be measuring deliverables when managing quality in projects. Another one of the 7 basic quality tools is the Pareto Chart. The Pareto Chart is essentially a histogram displaying the number of defects by type and has been prioritized from highest to lowest. It gets its name from an Italian economist named Vilfredo Pareto. While studying the distribution of wealth in various generations and geographical regions, he repeatedly found that 80% of the wealth was held by just 20% of the population, meaning just 20% of the people had 80% of the money. This became known as the 80-20 rule and has been applied to several other disciplines, such as quality management. In quality management, we find that typically 80% of the defects are developed from just 20% of the causes. The takeaway is that by fixing just 20% of the causes, we can prevent 80% of the defects. Typically, a Pareto chart may be developed in the control quality process and output as a quality control measurement. It will then be an input to the manage quality process where it can be further analyzed. The last quality tool we will discuss in this module is the scatter diagram. Scatter diagrams help us to understand any relationship that may exist between two variables. In our first scatter diagram, we will compare the effect that an independent variable, such as temperature, will have on a dependent variable, such as defect rate. Typically, the independent variable is found on the x-axis and dependent variable will be on the y-axis. In our first scatter diagram, it is difficult to find a clear relationship. Now consider a scatter diagram displaying defect rate based on humidity. The correlation between the data points indicates that generally, as humidity rises, so will the defect rate. Understanding whether or not a relationship exists can help with solving the problem. Typically, a scatter diagram may be developed in the control quality process and output as a quality control measurement. It will then be an input to the manage quality process where it can be analyzed.